in the last class, we talked about the spring element, the K matrix for spring element, how to do assembly if we have a system composed of multiple spring elements, how to apply boundary condition, and how to solve for the unknown degree of freedom, and also how to solve for the reaction force. So now today is a new topic, is the bar element. So I would say that most part for the bar element and spring element, they're the same. Because for one single spring, you can only apply force in x direction, either tension, compression. For one single bar, it can only carry, for this bar itself, it can only carry actual force, either tension, compression, right? So the only difference is K. So let's see. So in the textbook, is in chapter 1, section 2. You would ask your bar element. Again, we start from the simple situation. Let's assume that we have one bar and we have force applied at one end. It's clamped on the left side and force applied at the right side. And let's assume that the elongation is this red section. Of course, this is the exaggerated elongation. Normally, we would expect that everything we solve in solid mechanics in our undergrad class, they are within the elastic range, so deformation should be very small. But let's, for easy to see, let's put this as the elongation part. And we put the force applied at right side like this. Of course, for a bar element, it's not the same as like spring. You have the K for spring, and that's it. For the bar, you probably know the cross-section area, you know the length of the bar, you know what material you use, so you know the Young's modulus. So the parameter we can put it as, let's say if you know the material, you know the Young's modulus, and for the bar itself, you know the cross-section area. For tension and compression, only the cross-section matters, and the length of the bar we put it as L. And we put this elongation part, again, we put as delta. I'm pretty sure you learned from the previous class that this elongation delta equal to FL over EA. Are you guys working on homework or something else? What do you guys discuss about? So if you guys want to get a 10 bonus, you need to read this class. If you do something else in this class, I would prefer you not put it down your name, because this bonus part is really appreciation that you actually come to class and take the class. If you have any question, ask me directly. So this 15 minutes, you can only communicate with me, not with your friends or, yeah. So delta is equal to FL over EA. This is the equation from the first chapter of mechanics materials. Hope you guys do understand. And now, since our FEAK equal to F is like the relation between the force applied and displacement response, and there's a K. So we can rearrange this one as like force on one side and something times elongation, right? And that part in the middle should be the K for the bar element. So let's compare with what we have in the spring element equal to K times elongation data. And comparing these two equations, we can easily see that the stiffness K for a bar element equal to EA of L. It depends on the material used, it depends on the cross-section area, it depends on the length of the bar. And of course, this is only for tension compression. If we talk about bending, then we call it beam element, it's not bar element anymore, even though they're in terms of geometry the same. So K equal to EA of L. So this becomes the stiffness of the bar element. And of course, you probably learn from the mechanics materials for the tension compression, EA is actual rigidity. So it's like represent how rigid it is for the bar element to resist the force. If it's beam element, of course, it would depend on the material property, Young modulus, and moment inertia. So it's a different parameter, even though they are both cross-section area and moment inertia, they are the cross-section property. But if it's different force applied, we are using different parameter here. So if you check the textbook 1.2, this section, they will do the same similar derivation as spring element all over again. They take one bar element. So if this is positive x direction, I have node I, node j. So again, element force is the same magnitude of force, nodal force at node I and node j, and it should be the same sign at node j and negative sign of node I. So I have two equations, Fi equal to something, Fj, and we put two equations into matrix form, and then we have the equation for element matrix equation for bar element. The only difference is K equal to EA of L. And then if we have system with two bar elements, we do assembly, and then if there's boundary condition, we apply boundary condition. Sounds familiar, right? So it's basically a repetition. If you really want to read in detail, you can read the textbook. So just want to save some class time, I'm gonna skip all those repeated parts. You just imagine the only difference here, for the bar element, it is Young's modulus, cross-section area, and length of the bar, and everything else should be the same. So now we can, since we know it's the same, we can write for the element matrix equation for one single bar element, we can write as EA of L. I use superscript E to represent that specific element. And this 2 by 2 matrix for our 1D bar element is still 1, negative 1, negative 1, 1. And the same thing, node I is the first node, node J is second node. Every node have only 1 degree of freedom. And for the nodal force, element E and node I, element E and node J. Very similar. So since majority of things are same, so we can consider this equation can be used directly. Just be careful what is the K here. But of course, there are some difference because now K is determined by the Young's modulus by the cross-section area and length. So for, let's say, if we have a system with different, different parts, even though they have the same shape, same cross-section shape, or but if it's like made from two different material, the Young's modulus when they are different, it means the K different. So we need to discretize the, if you see, even you see it as one bar, you need to discretize based on the material. So a simple example, let's say if we have one bar. It has same constant cross section, but let's say left side is made of steel and right side is made of aluminum. And now in this situation, we need to have different section. So now at least this should be one node, and one node, and become two elements. It's not one element. So basically, when you have different Young's modulus or different material, we need to discretize into different elements. A bar can be discretized into a number of elements. Second situation is that, let's say if we have the same material, but it composed of different cross-section, then again, we need to consider them as two elements. So force. And of course, a typical example that FA becomes very useful is if you have a shape like this. So in this situation, it's really hard to calculate by hand. I mean, for this one, it's still doable by hand calculation. But for this one, you really need to use FEA with software, because now what you need to do is that you can discretize into different elements. So let's say so for this one, I can discretize this, use this average cross-section area as one section, and then for this one, I use smaller cross-section, and for this one, I use smaller cross-section. And of course, the more element you use, you are converging to the accurate results. So now our function of FEA software that you can use, you can do the convergence study to see how it changed. Let's say from 3, I just showed example, to 10, to 100, to 1000. It's hard, really, like you build a matrix and solve by hand or use MATLAB, but it's very easy to do using FEA software like Abacus or ANSYS. So this can be done using our FEA, and we need to discretize into different number of elements. And another situation is that, let's say we have the same material, we have the same cross-section area, everything is the same, but I have a force applied at middle point or any random point on this bar. It is possible. It is possible. In the spring element, you cannot do that. You cannot, like, you have spring element and you somehow apply. You can only apply tension compression at two ends. But for the bar element, it is possible that I apply a force at any random point inside this bar. It has same material, it has same cross-section area. In this situation, make sure that because we have the KQ equal to F, and F is always Fi, Fj, or any node. If you have n node, it's Fn. So remember that in our FEA, whenever there's a force applied, it has to be a node. Otherwise, there's no way you can calculate. So this means that even though this bar, it is one single bar, same material, same cross-section, you need to discretize this at least to two elements. This should be a node. So now this is element 1, this is element 2. Makes sense or not? Later, let's say in the beam chapter, it's possible, let's say you got calculus, like in the mechanics materials, you have distributed force on the beam in the transverse direction. in that situation, we need to find out the equivalent nodal force. So in our FEA calculation, always force, when there's a considered force applied, this force need to be a node. Or if you have distributed force, we need to find equivalent nodal force. Then we start the FEA calculation. So in this situation, we also need to describe into different elements. And of course, there are different things that might be a little bit different than the spring elements. The spring element, we calculate element force, but in the bar element, it is possible to ask to calculate stress, because if you consider structure problem in big picture, it's basically you apply tension and you want to know if it fail or not. So what do you need to do? It's not about the internal force, because internal force can be huge, but if I make cross section huge enough, it's safe, right? I apply force very small, it doesn't mean that it will break. So in the end, it's comparing the stress. So in the bar element, it's possible that we can ask what is the stress in the beam, in the bar element, instead of just asking about the element force or internal force. So how to calculate stress? How to calculate stress in the bar? Yes, thank you. Force over area. So same as previous step, in the previous class, we calculate internal force of the spring element, and with this internal force divided by cross-section area, you get stress. Internal force, when the positive tension, stress, same thing. You put a sign there, divide by cross-section area is always positive. So if it's compressive internal force, you get a compressive stress. If it's tensile internal force, you get tensile stress. So sign is always there. So now this is a complete theory part of our bar element. Of course, for the repeated part of derivation, you can check textbook or you can come to my office hour. So let's start an example problem directly. I use different color to represent different section, because the cross section is different. So it's bar system composed of 3 sections. So 3 sections, and it's clamped on both sides. We have force applied here. So this is a point, force applied at the middle point. And we have length of each section. I still use different color. So the red part, 0.3 meter. This side is symmetric, 0.3 meter. The center section, 0.4 meter. Cross-section area, for the red section, it is 10 to -4. And the same here, of course. And the black section, the center section, the cross-section area double. What else? So the force applied is equal to 10 kilonewton. And the Young's modulus of the entire section, the difference cross-section by material is the same. So Young's modulus 100 gigapascal. So we need to calculate displacement at center. Second, we need to calculate reaction force at left side and reaction force at the right side. Yeah, got the two questions. So how to solve, let's say first one, displacement at center. How to calculate, where should we start? Any idea? Set up the equation. What equation? Stiffness. Okay. Okay. So let's say for the big matrix equation for the entire system, what the dimension of K before we apply boundary condition? What dimension of K? What the dimension of the stiffness matrix before we apply boundary condition? 5 by 5. What is the dimension after apply boundary condition? 3 by 3. Yes, thank you. So the thing here is that even though it's really for the beam itself, without considering force applied, it is 3 section. But since there's a force applied at middle point, this point should be a node. Otherwise, there's no way you can calculate. Any constraint force in our FEA has to be at a node. So now this becomes a one node. So 1 element, 2 element, 3 element, 4 element. And we have 5 nodes. Node 1, 2, 3, 4, 5. And since we have 5 nodes, each node has 1 degree of freedom. So the K matrix, stiffness matrix for the entire system should be 5 by 5 before we apply boundary condition. And after we apply boundary condition, this one is gone. This one is gone. We have 3 by 3. Right. So now let's see the K. Well, as I said in the last class, I wrote the K for each element and then do assembly because that was the first example. But I think this example, we can skip that part. But I will still write the K for the red section and the black section, and then we will do the big matrix equation directly. So for the node, this is node 1, node 2, middle part node 3, node 4, node 5. And for the element, this is element 1, element 2. You discretize this one into 2 elements. This is element 3 and element 4. We have 4 elements, 5 nodes. So now let's say for the K for 1 and 4, they should be the same because they have the same cross-section area. They have the same length. Yeah. So for element 1 and 4, EA over L equal to let's convert everything to meter, Newton, and Pascal. So in the end, EA over L, the unit should be Newton per meter, right? Always be the unit in our FEA because when you start using the abacus, you will see that abacus does not give you space for really define the units. You need to be careful that what number you need to put in, and then you know what is stress unit came out from the abacus. So Pascal and cross-section area, and also use meter square. And length equal to 0.3. So the for the first and fourth element, 1/3, 10 to 8th Newton per meter. And for 2 and 3, obviously they are the same because they have the same cross-section area, same dimension. EA over L. Cross-section double, 10 to negative 4. What is the L for Mn2 and 3? 0.2, not 0.4. Be careful. Should be 0.2. Now we have the K for the 4 elements. We can write the structure matrix equation directly. Five by 5. I didn't do anything. I don't know what happened. U1, U2, U3, U4, U5. Right hand side, of course, becomes F1, F2, F3, F4, F5. To make it easier for you guys to see, let's put it into a different box. So I also put the column index here. So this is U1, U2, U3, U4, U5. Now let's see how to write this 5 by 5 matrix. How to write this 5 by 5 matrix. Start from element 1. What are the 4 components? Where are the location of 4 components? 1 and 2, right? So since element 1 is connected to node 1 and node 2, so in the matrix should be these 4 components. Make sense or not? And of course, we have a common coefficient 10 to 8 that we put outside of the matrix. So now it becomes, for element 1, we have positive, negative 1/3, negative, and positive. So this is for element 1. For element 2, we have is connected to node 2 and node 3. So the location matrix in this matrix should be these 2, right? So now we can write as, let's use a different color. +1, -1, -1, 1. Similarly, for element 3 is connected to node 3 and node 4. So it should be these 4 components. So again, we have +1, -1, -1, +1. And element 4 is node 4 and node 5. So node 4, node 5. We should have plus, -1/3, minus, plus. And for the rest component that there's no number there, it basically means there's no connectivity between those 2 nodes. We can put all 0. for the rest of the components. Any question? So you got clear about this, how we put this, write this 5x5 matrix? If there's any part that is like you feel confusing, please ask. Why was the center divided into sequence 2 and 3? So because we have force applied here, and in FEA, whenever there's a force applied, the point where the force applied should be a node. Otherwise, there's no way you can calculate, because let's say in the Q equal to F, in this F vector, when you put the force into the vector, it has to be F at node I. So whenever there's a force applied, this should be a node. That's why we need to discretize this one into 2 elements. Yeah. Any other question? Applied boundary condition. Since the boundary condition is at node 1 and node 5, so obviously F1, all the reaction force in FA are considered unknown force. So this F1 is unknown. It's not helpful for our calculation. So same as what we did before. We can remove this row. Similarly for F5 reaction force is unknown force. And since our U1 equal to 0, it's a wall, it cannot move. U5 equal to 0. So all the number that multiply by 0 doesn't matter. So now it becomes all these columns will multiply by U1, and same thing here, multiply by U5. So now this is how we apply boundary condition. Everything related to node 1 and node 5, they're gone. Any question? You can consider whenever the displacement is 0, it is a boundary condition. Yeah. Why did you cross out the top bottom row? Because this top row is for F1, right? So basically, how you do the matrix vector operation, this one times this one plus this one times this one plus this one times this one plus this one times this one for all the 5 components, right? And you get equal to F1. But F1 is unknown. So it's like you do this operation, it cannot give you any information. Make sense or not? And same thing for here. This one times this one equal to F5. But we should expect that, well, K is given. If you want to calculate this one, F5 should be given. But F5, again, it is reaction force is unknown. So this is also using this information. So that's why we delete the first and the 5th row, because F1 and F5, they're unknown information. And the way we delete these 2 is because, well, everything in this first column, they will multiply by U1. U1 is 0, it doesn't matter. Because it's reaction force. Reaction force is just unknown. The reaction force in FEA, they're unknown. Okay. That's important. Yeah. Yeah, it is important. Well, let's say let's forget about FEA, just based from mechanics materials. When you see this structure, do you know what is reaction force? Forget about FEA. Yeah. Anybody know what the reaction force? Using the mechanics material, not FEA. Let's forget about FEA for now. What is the reaction for the left side and right side? Okay. On the left side, it should be 10 kilonewtons going this way, and on the right side, 10 kilonewtons going this way. And time you mentioned let's write down what you just said. you said in the left side it should be 10 kilonewton to the right. This is fun. Right.
The left side should be 10 kilonewton.
This is what you just said, right?
Yeah.
But let's say if you do using statics, your structure is not in equilibrium. You have 10 kilonewton to the right, 10 kilonewton to the right, 10 kilonewton to the left. Your structure will accelerate to the right. 5.
No.
And from that moment, you'd be able to start.
20.
Yeah.
Yes.
You take a moment. How can you generate a moment? Your force is in the direction.
Would be 5 kilonewton to the
Thank you. Thank you. Do you want to explain?
Oh, I mean, the forces distributed between the 2 points, and like since it's right in the middle, it needs to be distributed evenly across the 2 points.
Yeah, there's a key information because it's symmetric about the structure is symmetric. Yes. Yes. So thank you. It should be 5 kilonewton. 5 kilonewton. Right. Now you have, again, it's nothing related to FEA. It's purely from statics, not even mechanical materials. You have 10 to the right, 5 to the left, 10 to the left. And it's half here simply because our structure is symmetric. Your force is applied at middle point, and to the right side, to the left side, to the right side, they are the same. Right. So this is from statics. How do we calculate the reaction force? But of course, in FEA, we always consider reaction force unknown force. Well, we can use FEA to calculate reaction force later to see if it matches what we had. So now we have the 3x3 matrix. Apply boundary condition. Let's write the 3x3 matrix here. After apply boundary condition, we have 10 to 8th. U2, U3, U4. How to write this vector here? Yeah, number.
0, 10,000, 0.
Yes, thank you. So I got a question before the class about your homework. Whenever there is no force applied at that node, you consider it's 0 force in your equation. So same thing here. Should be 0 at node 2. And given force applied node 3, 10,000 Newton. I put everything as Newton and meter. So we can solve for U2, U3, U4. -10 to -3 meter. I use millimeter directly. And of course, the question asked about the displacement at center. So yeah, it's U3.
Show that how we solve displacements. Do you do like the inverse method, or do we just do it like the middle school old-fashioned way to solve the displacement? Do you care how we do it?
I don't. Because those part is not really FAA content. So, and of course, as I said in the first class, in the homework, you are expected to solve 3x3. But in the exam, I will do my best to make it 2x2. So it's not gonna be like spend a lot of time just for calculation. I really don't care about calculation part. And you don't need to show me like inverse of 2 by 2 times the vector. Whatever you can solve the two unknowns, that's fine. Any question for this part? How to calculate reaction force in FEA method? Yes, yes, thank you. Now we can go back. Let's say oh no. This one equal to reaction force at left side, reaction force at right side. Right. Now we have U2, U3, U4 solved. We have U1, U5 equal to 0. So simply this one times this one equal to F1. And this one times this one equal to F5. F5 equal to R right, F1 equal to R left. So let's see. F1 equal to, we have 3 zeros, so only first two component. And since, okay, U1 equal to 0, so only one component. It's only this one times this one. Right? All the rest are 0. So negative 500 Newton, it matched. Right? Negative means to the left. 500 is half of the 10,000 we applied. Oh, 5,000, sorry, it's not 500. And similarly, the reaction force on the right side equal to F5. And to go back to our equation, you can see that 0 U1, 0 U2, 0 U3, negative 1/3 U4, 1/3 0. So again, we only have one component. This one times this one equal to F5. Any question? What if I ask you the, let's say, I give the allowable strength of the material and ask you to check if the structure is safe or not. Yes, yes, yes. So in that situation, what we need to do is that we need to calculate the stress in each member. How to calculate stress? Potential compression is force, internal force divided by cross-section area, right? So since we already have all the displacement, you can easily calculate internal force is equal to K, and we have the Uj minus Ui over the second node minus first node. That becomes the internal force, and that internal force divided by cross-section area, you get the stress. And compare that stress with the allowable strength of the material. You can check if structure is safe or not. Make sense or not? Any question for this whole section? So if no question, we're done for the, I think we only have 4 minutes left. Thank you for coming and have a great weekend.
Other than nothing.
Yeah, right.